So Unit 2, important concepts in Unit 2. The first thing we talked about was inertia, Newton's first law. Okay? There's not any calculating to do with that law. Okay? It's simply what an object does when there's no net force acting on it. What does an object do when there's no net force acting on it?
So if it's like staying still, if it's not acting on it, it stays still, and if it's in motion, unless it's acting on it, it shouldn't.
Right. An object at rest will remain at rest. An object in motion will continue in motion at a constant velocity. Okay? There is basically no acceleration unless there is a net force. Newton's first law deals with all situations where there is no net force. So there is no calculating to do with Newton's first law. But there could be multiple choice questions about it. Then we talked about the most important thing in this unit, Newton's second law. Okay, F net equals m times a, which is the vector sum of all forces. We did all kinds of Newton's second law types of questions. We did static questions. What's the net force in a static question? 0. Yeah. So an object is hanging, or an object is traveling at a constant velocity, or the two sine, the two cables and the one sine kind of questions. Okay? Those are static questions. We talked about elevator questions, where you got the tension in the cable pulling up and gravity pulling down. Those were all pretty simple ones. Okay? Then we got into more complex stuff where we had to do vector addition. Okay, so we have this vector and that this force that's moving at 30 degrees north of west, and this force that's moving due north. Calculate the acceleration of the object. Okay, well then I have to draw them tail to head. So we could have had a few like that. Okay, we went into inclined planes. We talked about systems, and then we talked about like friction after that. Okay, but we dealt with all kinds of different situations. Okay. What's my favorite kind of Newton's second law question? Yeah, ramps, inclined planes. I like the Taylor knows me. I don't know if I like the rest of you as much. Okay. So yeah, think about inclined planes. Okay. In fact, let's do a question on inclined planes right now, but I'm gonna make it hard. So it incorporates two things. Okay, I have this nice frictionless inclined plane with a pulley on the top. I have an 8 kilogram mass sitting on the ramp and a 5 kilogram mass hanging over the pulley. I want to calculate the acceleration of the 8 kilogram mass. Let's see how much we remember. So first thing we need to do is identify all the forces that are acting. Okay? And the first force that's acting is the force of gravity pulling down on the 5 kilogram mass. And that's 49.05 newtons. 5 times 9.81. Okay. The ramp's frictionless, but it's a ramp, and we're pulling something uphill. So there is an F parallel that is going to be working against the force of gravity from the 5 kilogram mass here. Right? If I want to calculate that, then I've got to do the usual inside the inclined plane triangle. We've got force of gravity, we got normal force, which we won't need, and we got F parallel down here, and this being a 30-degree angle. All right, so our force of gravity is 78.48. Okay, 78.48 newtons, 8 times 9.81. Now if I want to get the force parallel, I go sine of 30 times that. Okay, and so it's going to give me half of that, right? What does that parallel come out to, you guys?
39.1.
39.24. Okay. So. All right, so I've got now the two forces that are involved in this calculated. But because there's a pulley, this is a system. All right, what do I need to remember about systems? It all accelerates at the same rate, or the net force acts on all of the mass in the system. So the 5 kilogram mass and the 8 kilogram mass have the same magnitude of acceleration. What's different is the 8 kilogram mass is going to accelerate up the ramp, and the 5 kilogram mass is going to accelerate straight down. And the question did ask, what is the acceleration of the 8 kilogram mass? So now what I need to do is essentially simplify this diagram to represent the entire system. 13 kilograms being pulled one way by 49.05 newtons and the other way by 39.24 newtons. All right, now I can do the vector sum of all forces, okay, and calculate my F net, which would be 9.81, right? Okay, so my net force is 9.81 newtons up the ramp, or whichever, to the right, whichever. Okay, so there's my net force. Now if I want to calculate the acceleration of the system, I take my net force and I divide it by the mass, 13. Okay, so my acceleration is going to be 0.75 meters per second squared. Actually, I only have one significant digit, so it'll be 0.8 meters per second squared up the ramp, because it did ask about the 8 kilogram mass. Is that ringing a bell for everybody? Right? So nothing mathematically difficult in that question, but there's a few conceptual things in there that you would have to remember from Unit 2. You have to remember how systems work. You have to remember how inclined plane works. Okay? Vector sum of all forces was in there. Right? That's a question that tests a lot of different things all in one question. All right, so lots of Newton's second law stuff, could be a variety of different things, and a few multiple choice questions just about how F net equals m times a. So, you know, what if you increase the mass of an object? What effect would that have on the acceleration if the force didn't change? Or if you doubled the force, what would happen to the acceleration if the mass didn't change? Stuff like that can come up in the multiple choice part, okay, of the final exam for that. Okay, questions there? Then we talked about Newton's third law. There are no multiple boxes being pushed questions on the final exam. But there are a couple of multiple choice questions about how Newton's third law works. And every action has an equal and opposite reaction. That we need to know. Okay, fourth thing we went over, work energy theory. Second most important concept. So work's a change in mechanical energy. And that means force times distance equals our final mechanical energy minus our initial mechanical energy. Further expanded out to be initial potential, final, and all that the final potential plus final kinetic equals, or sorry, minus, okay, initial potential plus initial kinetic. So a question like that could work something like this. Okay, so I could give you a situation like this, okay, where I tell you the final speed, the final height, bottom of the ramp, initial height and initial speed, and either I give you the length of the ramp or I give you the angle, okay, doesn't really matter which here. Let's just say the length of the ramp is 12.5 meters. And I would ask you, calculate the force of friction, okay? Because this thing should just slide down the ramp, okay? But if it slides down the ramp and the ramp is frictionless, it should have the same amount of mechanical energy at the bottom as it does at the top. But in this case, that is obviously not the case. It's barely going faster at the bottom than it was at the top, and it's fallen 3 meters, 3.1 meters in fact. So it should be going a lot faster than that, but it's not. And the reason for that is it's losing some of its energy to friction. It's doing work against the force of friction. Okay? So I'm going to give you a few minutes there. You're looking for force here. See if you can figure out what the force of friction is on this one. This would be probably one of the easier ones you would get. In class, we did ones like this where I told you the force of friction and made you calculate what the final speed was or the initial height was or something like that. So that mass I was supposed to give you is 12 kilograms. And it's also 12 kilograms at the bottom. Pardon? No, it won't, because mass is force line. Yeah. All right, so we're trying to calculate just the force of friction, which is the only force acting here. Okay, so all we have to do is basically fill in our numbers for the rest of this. Okay, so what we're going to have here is the force of friction is going to equal the change in energy divided by distance. So that will be m times g times h final plus 1/2 mv final squared minus mgh initial plus 1/2 mv initial squared, and then divide that by d. Okay, that's what we're going to be looking at for a formula. We just have to plug in all the numbers. So that's going to be 12 times 9.81 times 0, which I didn't need to bother writing, but I did anyway. Okay, plus 1/2 times 12 times 2.2 squared minus 12 times 9.81 times 3.1 plus 1/2 times 2.2, or sorry, times 12, okay, times 2.0 squared. And we're going to divide all of that by 12.5 meters. Okay, so 12, actually we won't even do that. 0.5 times 12 times 2.2 squared gives me that. All right, minus 12 times 9.81 times 3.1 minus, or sorry, plus, oops, I shouldn't have done it that way. Okay, plus 0.5 times 12 times 2 times 4 basically. All right, so there's my change in energy over the entire length of the ramp. Okay, if I divide that by the length, okay, force of friction is negative, and it should be, it's resisting it. Okay, 24 point, well, actually we only have 2 significant digits there, so it'd be 25 newtons. All right, everybody okay with that one? All right, after work energy theorem, we talked about conservation of mechanical energy. Okay, those are EI equals EF kind of questions. So if we, yeah. You know what? It's probably because I pressed equals in the middle here. Let me try it again. So let's just do it over.
Because you didn't go like the second half of the graph.
Yeah, I did. But yeah, I did it in 2 separate steps. 0.5 times 12 times 2.2 squared minus 12 times 9.81 times 3.1 plus 0.5 times 12 times 4. Yeah, that's a different number. Okay, and then we divide that by 12.5. Is that more like what you got?
Yeah.
My bad. Okay, so conservation of mechanical energy, roller coaster questions, okay, sled going down a hill kind of questions, okay, where there's no friction, right, and energy is conserved between top and bottom. How will you know the difference? Because conservation of energy and work energy theorem give you a lot of the same information. What will a work energy theorem question either give or ask for that you will never have in a conservation of energy question? Force, yeah. You might have distance because it could be change in height, but you'll never have force in a conservation of energy question because the only force in a conservation of energy question is gravity. And the other force would be doing work on the system, okay? Either increasing its energy or decreasing its energy. So you'll never get force or be asked to calculate it in a conservation of energy question. It will, however, be a big part of a work energy theorem question as work is force times distance. All right, that's really about it. Okay, we did talk about friction. Okay, that's in there as well. I guess I should skip over that, but there's part of Newton's second and third laws. Okay, so force of friction is mu times the normal force, which obviously was part of Unit 3 in terms of unbanked curves. All right, so that's a big part of that. Could have a question that involves having to use coefficient of friction. There's a few multiple choice questions about the nature of friction. Okay, but that's about it. Right. That's it. That's what's in Unit 2. Anything else you want me to go over? Do you want to make a conservation energy problem for you to try? Okay, person's on a sled. That's a toboggan sled. Okay, and they're headed down the hill. Something like that. Okay, all right. So Okay, I want you to calculate the height of the hill that this person is sledding down. Their initial speed is 3.2 meters per second, their final speed is 18.5 meters per second at a point 3.5 meters above the bottom of the hill. Okay, give you a few minutes on that. All right, so on a conservation of energy question, okay, we got EI equals EF, okay, and then we go from there to outlining the different types of energy, okay, and doing the calculations. Okay, so for this one, that's going to mean initial potential plus initial kinetic equals final potential plus final kinetic. What we're looking for is part of the initial potential energy, so right away I'm going to subtract the initial kinetic over to the other side, and I'm going to be left with this. M times G times H initial equals M times G times H final plus 1/2 MV final squared minus 1/2 MV initial squared. Since M is in every term, it will cancel, which is good because you were not given it in the question. And I just need to solve for HI, which means I divide both sides by G. And then I can plug in my numbers. So my initial height will be 9.81 times 3.5 plus 1/2 times 18.5. Okay. 5 squared minus 1/2 times 3.2 squared divided by 9.81. All right, so the initial height of the hill is 20 meters. Okay. Questions on those? All right. Okay, so tomorrow I will go into detail about the final exam itself, number of questions, all of that kind of stuff, talk about exactly what will be on there so you can really focus your studying for Friday, because I know it's kind of a quick turnaround for you. And then I'll take any other questions from you. So if you guys come with questions tomorrow, you'll get a heck of a lot more out of it. Okay? All right, get those desks cleared off. We'll come around and pray.